Hello again, everybody. This is going to be physics video number 3. Took a little time to make a nice looking graph area. Except did a little wiggle right there. Sorry about that. But normally when I do this in class, I probably won't spend as much time making it look nearly as nice. But I wanted to introduce a new concept for you. The concept of the distance time graph. We'll also do a velocity time graph. You're going to need to be able to be good at expressing an object's motion in a graphic format. In order to interpret these, in order to watch an object moving and then turn it into a graph, or the opposite, looking at a graph and figuring out what does that look like in the real world. Okay, you need to be able to do both of those. You need to be able to interpret what do distance time and velocity time graphs look like. Just a couple of real quick basics. Time always on the horizontal axis, all right? Because it's an independent variable, time is always going to be happening. We don't really adjust time. Unless we do some time travel, but we got dozens and dozens of movies explaining why we shouldn't do that, right? From Back to the Future all the way through, Avengers, right? So anyway, time we call an independent variable. It always continues to happen. However, distance, okay, this will change depending on an object's motion, all right? So here's how it's going to work. We're typically going to be measuring time in seconds, okay? And let's say we're going to measure distance in meters, all right? So that means that I'm going to try to make this look decent the first time so that I can reuse this graph later. Here's some marks. Hopefully they're pretty close to equidistant from one another. All right, so here's an amount of distance. We're going to need an amount of time as well. Okay, so we're measuring time in seconds, measuring distance in meters. So let's say we have an object that is moving at a speed. Because we don't know the direction, we're just going to go with a speed. Let's say object number one is moving at 1 meter every second. Okay, it's moving at 1 meter every second. Object number one moves at 1 meter every second. So obviously, if we're going to call this the 0 point, all right, at the origin, that means that after 1 second of time, let's go ahead and mark the 1, 2, 3, 4, 5, 6, and 7. That means we also need meters in 1, 2, 3, 4, 5, 6, 7, up to 8. All right, so let's say object number one moves 1 meter every second. That means after 1 second, the object has moved 1 meter. We put a dot, right? Standard graphing type stuff. After 2 seconds, it's gone 2 meters. 3 seconds, 3 meters. I think you get that. So we would expect a line that kind of looks like a slope of 1 meter every 1 second. It rises 1, it runs 1, right? The rise, right, is the distance in meters. The run is the time in seconds. Okay, my 4 looks kind of funky there. So anyway, rise over run. If it's rising 1 meter, it's running 1 second, meters per second, meters over seconds, rise over run. Do we see how all this kind of comes together now from our algebra classes, right? Well, let's say we have another object, and I want to graph it, but let's see. Do you want to go faster or slower? I'm old, so it has to go slower. All right, so let's say this object is only going 0.5 meters per second. Okay, so this object is going half the speed of the previous one. I mean, I think we get that just from the numbers. But what does its graph look like? Well, after 1 second, it's only traveled half of a meter. So it hasn't gotten to the 1 meter mark yet. It's only gone half of a meter. That means that after 2 seconds, it's finally crossed the first meter. And so obviously the slope of this line is less than the slope of the previous line. Now, yeah, my lines are a little wiggly. I agree. I also don't have grid marks all throughout this page. So that's where graph paper is obviously much more helpful. But the point being, a distance time graph with a shallow slope, right, where it's not a very steep slope, it's a shallow slope, means an object is not covering as much distance for every unit of time. The steeper the slope of an object, okay, means that that object is covering more distance for every second of travel. All right, so on a distance time graph, the steeper, the faster, the shallower, the slower. Let me reset. Okay, we're back. I just reset because I want to consider a different type of graph called the velocity time graph. So velocity is going to be measured in meters per second. Time is going to be measured in seconds. These graphs are going to look different. They're a little harder to interpret, I find. Most students find these a little bit trickier. So that's why I want to spend a little time explaining the ins and outs of a velocity time graph. So let's say we have, let's start the opposite way because that helps as well. Let's start with a graph and see if we can figure out what it means to have that. Okay, here's our first graph. Object number 1, all right? So in blue, object number 1, we have a velocity time graph here. And so what you're going to see is velocity measured in meters per second, all of these numbers on the side here, right? And then the amount of seconds across the x-axis, as always, all right? So time on the x-axis. At every time interval here, at 1 second, at 4 seconds, at 7 seconds, whatever, it seems like this graph is always at 6. So is this object moving? Something we need to understand. Is this object even moving? If its velocity is 6 meters per second, yeah, it's going. It's got a velocity of at all times in this graph, its velocity is 6 meters per second. Let's try a different shape. I'm going to stop here for a second and analyze this first part of this line. So we have this green line. This is object number 2. So obviously, this is a little bit different because this one connects to the origin. So at time 0, the velocity is 0. But at time 1, the velocity is 1 meter per second. So it's gone from a dead stop, right? 0 meters per second is a dead stop. Gone from a dead stop to now moving 1 meter per second. After 2 seconds, pretty close to 2 meters per second. So now, not only has it started moving, but it's getting faster. It's accelerating to 2 meters per second. At time stamp 3 seconds, it's now pretty close to 3 meters per second. So this object has gone from dead stop and it is accelerating. It is getting faster every second of travel here. For the first 3 seconds, it's speeding up. Now let's say the graph continues, but changes in the way it looks. All right, so now this graph, still the same in the first 3 seconds, but now for the next 3 seconds, this graph is different. Why is it different? What's it done, right? This graph has now got 3 meters per second at second number 3. At second number 4, also 3 meters per second. 5, 6, 7. Every second so far after that, it's still at 3 meters per second. So this object is still moving, which is key, right? This object is still moving. It's just not getting faster anymore. It's not accelerating anymore. The acceleration is the key here, because with a velocity time graph, we're not calculating an object's speed or velocity. It's showing the acceleration of the object. So if we go back to object number 1 here, if it starts at 6 meters per second, right? Do you remember the formula for acceleration? I'll probably put that up here. Acceleration is delta V, right? So it's the change in velocity, which means final velocity minus initial velocity divided by the time it takes to do it. All right, so acceleration is the change of velocity. How quickly does velocity change? Well, for object 1, that means final velocity was 6 meters per second, right? Initial velocity was 6 meters per second. Time, we could say, was 7 seconds, if you wish. But the point is, 6 minus 6, obviously 0, so our answer here is a 0 acceleration. This object does not accelerate, okay? It stays moving, it's still moving, it's just not accelerating. It's not getting faster or slower, it's staying at the same velocity. Now object 2. Let's tell you what, let's focus on the first part first, okay? So we're just gonna concentrate on the first 3 seconds first, because I'm pretty sure we can already calculate the acceleration after 3 seconds. Let's focus on the more interesting part of this graph. Here, this is basically a slope of 1, because it goes from 0 meters per second. So let's go ahead and set up this formula. I'm going to do it over here on the side so I have enough room. So the acceleration in the first 3 seconds only. Acceleration, final velocity minus initial velocity divided by the time it took to do the change. So final velocity minus initial velocity divided by the time it takes to do that change. The final velocity of this object was, let's say 3, although it's not perfect because my lines aren't exactly straight, but let's call it 3. 3 meters per second was the final, and the initial connected to the origin, the initial is 0 meters per second. And how long did it take to make that change? 3 seconds. So obviously 3 minus 0 is still 3. Divided by 3 is 1. But now the unit. With accelerations, units should be 1 meter per second squared. Do we see why it's meters per second squared? When you have meters per second in a numerator and you divide by more seconds, it becomes seconds squared in the denominator, okay? So accelerations typically have a time unit squared in a denominator. All right, so look for that. If you see that, that's a good way to recognize that this is probably an acceleration. If the time unit is squared in a denominator, it's probably built on some type of acceleration. A distance divided by a time squared, okay? So a couple of graphing exercises today. We'll practice this with real objects and graphs in class, all right? But I want you to be good at interpreting distance time graphs and velocity time graphs. That's all for this video. Thank you very much. See you next time.